We can start our first session after the break. So the first speaker is classmate Maxwell, talking about gamma factory status and physics highlights, please.
Is it now on? Okay, okay. So I want to start by saying that I am very pleased to talk to people and not to computer screens. As Misha was saying, this is very important that we are coming back to the normal way of presenting our talk. And since my talk is very different with respect to Misha's, I would like to start with a general transparency, somehow to make the transition into something which is the content of my talk. If you think about the future of high energy physics, then you look at the past of physics, and you notice that there was always a correlation of the progress that was made with new concepts and new tools. And I just gave you two examples of the developing of the tools with respect to equations. And I'm using this transparency also to recall, you see, the person who died, who passed away last year, who was Freeman Dyson. To put it, you see the relationship between the progress which is driven by concept and tools in a very nice way. He was saying that the new directions in science are launched by new tools much more often with respect to by new concepts. And he added that the effect of concept-driven revolution is to explain all things in new ways, while the effect of a tool-driven revolution is to discover new things that have to be explained. So in that context, I've spent a significant fraction of my time of what kind of tools the Gamma Factory, the project which we are developing for the last 5 years at CERN, what kind of tools we could bring to the research at CERN. And then, if I have time, I will give you some examples of physics highlights of this project and on the Gamma Factory status. What is Gamma Factory, for those of you that have never been confronted with this term? So the Gamma Factory is basically the infrastructure and the operation mode of the CERN accelerators, which allows to produce, accelerate, cool, and store beams of highly ionized atoms in terms of particles. You would like to accelerate and store atoms. And you would like to excite the atomic degrees of freedom by laser photons to form high-intensity secondary beams of gamma rays, and using those gamma rays to produce diverse tertiary beams that I will explain you what kind of beams we are going to produce. And of course, it has a part which is the research program, which is in the broad domain of science, which could be enabled by having those tools. This is saying the same, but in the pictorial way. So far, we are running at the LHC protons and also protons with neutrons, which are confined in the nucleus. Our project Gamma Factory has already proven that we can produce atomic beams directly from the source and control the number of electrons which are left attached to the nucleus. And we have proven that we can accelerate those beams up to the energies of the LHC and keep these atomic beams, which was not evident, for of the order of 40 hours in the LHC. That means that these beams are ready to be used in the experimental program. So the next steps that we are planning is to excite those beams with lasers. And we are preparing now the experiment that would run first at the SPS, which will be the proof of principle experiment, in which we would try to excite for the first time the moving beams of atoms. So the research tools of Gamma Factory are the research tools which are made out of light. So in that sense, they are new. I will mention 5 principal tools that we are going to introduce if this program runs at CERN. First of all, you know the techniques of atomic traps, which has been used, for example, to prove the Bose-Einstein condensation of the atoms of the sodium, or for example, how you construct atomic clocks So the gamma factory would provide you for the first time new type of atomic traps in which we can, for the first time, trap highly charged ions. That means the ions, think of the lead nucleus with large Z and 1 or 2 electrons. So those atomic system has extremely strong electric field. So you can probe with a very high precision the QED vacuum effects. And those are small size atoms. The size of those atoms are something like factor 100 to 1000 smaller with respect to hydrogen atoms. We approach your electrons with the nucleus so you can look for electroweak effects in the atomic physics. Now, having the simple structure of large Z atoms with 1 or 2 electrons makes the calculation of the process is very simple because the hydrogen or helium-like atoms are very easy to calculate in terms of the theoretical prediction. So we hope to improve several measurements in the standard model with the atomic physics approach. And what is very important that thanks to the fact that our trap, contrary to the traps that have been constructed so far, moves with very high gamma Lorentz factor, we can use the Doppler effect and excite even the deeply bound electron with visible light coming from the laser. So this is the profit that we get from the fact that our trap is not stationary, but it is a moving. Of course, we send this trap over 26.7 kilometers of the circumference of the LHC. So if you put the atomic clocks in such a trap, we can hope to test the basic law of physics, like Lorentz invariance test, or we try to detect, for example, gravitational waves. The second tool that Gamma Factory can provide is that something that you a little bit miss at the LHC, which is the collider of protons and nuclei. And by having atomic beams,
gamma factory.
Better. So the last thing that I only mentioned for those that know the limitation of hadronic machines in terms of luminosity, I would just mention that the atomic beams allows you to cool the beams to extremely large degree and break the you see the limit which comes from the necessity of collimation of the beam. So for everything that has to do with large intensity hadronic beams, the gamma factory is the way to go. So the physics with gamma factory tools extends to many branches of science. It includes particle physics, accelerator physics, particle physics, and also applied physics. For those that would like to know a little bit more, you see, we are now making this joint effort, you see, to have a special issue of Annalen der Physik in which we would address all the questions that gamma factory could address. I just put a couple of transparency with the papers that we published this year, you see, in terms of what gamma factory could do. So I will spend my second part of the talk, you see, on the couple of examples, because I cannot cover, you see, all the domains in all the branches of physics that gamma factory could do. So first of all, probably what I consider important for this audience is that gamma factory could contribute to high luminosity LHC in the sense that, you see, there are two ways of making high luminosity, and there is the first way in which you basically change the sizes and the divergence of the beams by working with the focusing power of the beams in the interaction point. And this is basically the ongoing high luminosity PP LHC project, which for the cost of €1 billion is expected to give you the luminosity which is larger than 10 to the 34 1/centimeter squared per second. So there is also another means which is enabled only by the gamma factory. That means that you can cool those beams, and instead of working with the beta of the focusing power of the machine, you decrease the emittance of your beam. And this is the paper in which we actually analyze what gain we could make by going to this scheme. So basically, the gamma factory scheme of reducing the transverse beam emittance and going to large luminosity without necessity of strong focusing is to produce highly charged ion branches, leave the electrons, they cool the beams by taking into advantage that the electrons are still there, and we can shine only on the fraction of the ions. And you see, the technique is very similar to the technique of cooling of alkali atoms. And then you basically, you don't need those electrons any longer. So we cool at the SPS at the top energy. Then we strip the electrons in the LHC transfer line and accelerate and collide fully strict ion beams. So in this paper, we went through all this, you see, stages, starting from the source, you see the cooling phase and the injection into the LHC. And we found out that we can achieve with the scheme comparable luminosity to the one which is the luminosity of high luminosity LHC. And the cooling time, which we'll have to make the cooling at the top SPS energy are of the order of 10 seconds. So you see, you can reduce the emittance of the beam by factor 10 over more or less 10 seconds. Now, of course, this method cannot be used to cool proton beams. But my point here that I would like to mention only is that, you see, if you run, for example, calcium beams, thanks. Then you see all the experiments that were deep dynastic experiments that were building the standard model in which I participated personally were made with isoscalar beams. So in some sense, for electroweak physics, running isoscalar beams, which have similar, the same number of protons and neutrons, is much more favorable. Just to draw your attention to that, the U and D quarks have different charges, weak isospin and vector and axial coupling. So the proton, which is 2U and 1D, is not the, it's you see, this is SE for electroweak physics. You would have the beams of mixed beams of neutrinos and electrons with not precisely known proportion. So if you go to isoscalar beams, you basically equalize the distribution of U and D quarks. So that means that you still don't know what is the, you see, you just make them equal, the proportion of neutrinos and electrons in some sense. So that's why you see most of the precision program that has been done in the 70s, 80s, and 90s were made with isoscalar beams. So we are happy that we will be able to pull isoscalar beams rather than protons, because we can achieve much higher precision in the measurement at the LHC. But not only that, you see, if you collide, you see large Z particles, then, for example, you have a very large leap in photon fluxes due to the force. So we can actually have in this gamma factory driven scheme access, for example, to exclusive Higgs production in photon-photon collision mode, not mentioning the fact that you see we would have significantly lower pileup backgrounds, which is the limitation coming from the detectors at the LHC. So the example number 2, which I probably only mention, is that the gamma factory we are developing now this the polarized muon source and neutrino source, and this is very important because you see, as I put here, who would not be excited by the perspective of constructing of 3 TeV muon collider in the existing 7-kilometer SPS standard for the cost of 5.5 billion Swiss franc, which is actually the cost only of digging the tunnel for this 100 kilometer long 300 GeV E plus E minus collider. And there is lots of work going in this direction now, how you could actually construct this muon collider, and you see on the way how you would construct the neutrino factory, which would be based on the decays of muons. The gamma factory contribution here is to revisit the question of whether you would need a proton driver for this machine, whether you could replace the protons by photons, and also how to avoid the cooling phase of those beams. So this is the, I will probably not go into details of this scheme unless you ask the questions, because my time is running over. I would only stress that the muons which are produced by the gamma factory are polarized, which is very important, yes, for this physics. And what is also important that you see the emittance of our beams is such that they can be immediately accelerated. And for the neutrino factory, you see, we would have already ready beams of high intensity muons. There is, of course, the full domain of for the gamma factory of having such an incredibly high flux of the photons. You see, just to give you a comparison, we would have for all kinds of beam dump experiment for the searches of very weakly interacting particles like axions, or for example, dark photons. We would get something of the order of 10 to the 25th photon on target, which, for example, has to be compared to the canonical number for ship experiment, which is being planned at the SPS with the number of protons on target, which is of the order of 10 to the 20th. So this opens many possibilities, and you see the limits on the arc are really extending much below, in terms of coupling constant, the existing constraint. So I just finalized by showing you 2 slides. First of all, the gamma factory now grown to something like 100 people team, and we are working within the CERN physics beyond collider framework. And we already, out of our 6, you see, milestones, we already reached the first 3, and we are now in the last phase of forming the collaboration for the proof of principle experiment at the SPS, in which we would test the interaction of this partially stripped ion beams with the laser. And it will be on that basis that you would like to extrapolate the results of this test to the LHC and prepare the technical design report for the LHC-based gamma factor. So this is my conclusion. Gamma factory can create at CERN a variety of new research tools, which could open, say, new research opportunities in very broad domain of basics and applied science. And if you are interested, I have given you a couple of examples of papers that you can go and read and find out what we could do better with respect to. The point is that it's very rarely that you can say get, you see, the increase in terms of fluxes by 7 orders of magnitude. So it's always, you see, when, say, for example, Galileo invented new way of looking at the stars, that discoveries were coming here. So this is why I put my first transparency of the relative balance of the tool-driven revolution and concept-driven evolutions, thinking that we are now in the stage in which we do not have that many new concepts that would bring us with, you see, new ideas where to go. So it is the very right time to start thinking what kind of tools we would like to develop in order to ask new questions, because you ask new questions only if you have new tools. Another point which is very important, that the gamma factor research program can be largely based on the existing accelerator infrastructure. The investment in terms of laser system is not that costly. It's much less important with respect to the cost of major experiment at the LHC. And this is what I would like to stress once more, that the quest for diversity of research subject and communities, which is specific for the gamma factory, because we are bringing atomic physicists, you see, nuclear physicists to this program, is of particular importance at the present phase of accelerator-based research, as we neither have any solid theoretical guidance for a new physics just around the corner, which are accessible by the FCC or CLIC, nor an established and reasonable cost technology for the leap into very high energy, you see, colliders. So in this configuration that we are now developing of such products, at least to me, makes sense. And of course, gamma factor requires extensive R&D studies, including its proof of principle experiment, which we are preparing now, which must be finalized prior to the next European strategy upgrade, such that you see this program somehow gets into the common way of making the programs being realized. Thanks.
Thank you very much. Question, please. Yes, Bogdan, please.
Thank you. You mentioned 3 mu plus, mu minus at CERN, collider with polarized muons.
Yes.
Can you say?
You see, 3 is a number which is not, you see, there are several ways of thinking how you would do it. 3 is something that you would get with the existing magnet technology if you would like to use the empty space of the SPS. Whether this is the correct energy, I don't know. People are thinking of 16 TeV in the LHC tunnel, you see. So it is not at this stage, you see, but if you would think of 3 TeV with existing magnet technology, you can put such a collider in the SPS tunnel, and there's plenty of space because SPS is large. And if you have ever been to the SPS tunnel, there's a place you see to put the ring of muons.
Matthias.
I hope I understood this correctly. Did you mention gravitational waves at some point in the beginning of your talk?
Yes.
Could you elaborate a little bit what you have in mind there?
You see, you can put atomic clocks, and then you make the atomic clocks into a circular motion. And then if you would have any, you see, and you just count the ticks, you see, of the clock. If the gravitational wave would deviate the space-time, you see, for the passage of the beam particles, you just have some filter, you see, in terms of. So since this is, you can keep those beam for 10 hours, you see, more or less. you can use, for example, thorium-based clock and just send it around and probe, you see, with external beam of photons, you see, to find out if you have this.
Studies what type of frequency range one would be able to probe in this way?
I don't know precisely now. You see, we are starting this studies. And if you are interested, please join here. You see this.
Very exciting. Yeah.
This studies. Yes. Yeah.
Last question.
Right. So I try to understand what is your main goal here. Is a gamma factory or is also gamma collision also in
Yes.
on that?
Yes. Yes.
Have you calculated how?
Yes. So
interactions are set up?
yes. So in the context of so the maximal energies of the gammas would be 400 MeV, given the present energy of the LHC. So you can collide those gamma beams with counter-propagating gamma beams. So the maximal gamma-gamma collider energy would be 800 MeV. But you see, this collider would not have very large luminosity. It will be of the order of 10 to the 31, 10 to the 32. But you can collide those beams of the gamma factory, for example, with the photons, which are stuck in the Fabry-Perot cavity. For example, for birefringence kind of test, or for example, for the punctual searches of dark matter particles. The dark matter search in the gamma factory would be first made with the sending the gamma factory beams on that fixed target, in which you basically use the photons, which are classical photons from Weizsäcker-Williams, you see, of the atoms. But if you see something, then you can tune the beam of another gamma beam with respect to the beam of the gamma rays, and you can have the monochromatic collision of the photons, which would cover the span of the energy in between, you see, 1 keV up to something like 1 MeV of the collider. But this collider would have now the luminosity of 10 to 37 or 10 to 38, incredible luminosity. So if there would be any, for example, arc type of particles to photon by a kind of effect, you see, you can actually tune the gamma factory beams and the lasers that you have, for example, the normal visible laser or a free electron laser, to really look for the tiny bit of the energy scale.
You require physics to see this.
You require, so this would be only, you would go to this if, for example, we cover this extended space for dark photons and axions, and we find that we observe a signal. And then you go to the next phase, like between hadronic colliders and electron-positron. You tune two beams of photons by going exactly to the resonance. But at low energy, this requires, you see, that there is something interesting. But there are several models now of the dark matter. I will not give any judgment whether they are correct or not, you see.
Okay, yeah, I think we should.
No. For G-2, this project gives you the source of polarized muons, which have very low emittance. You can form the beams, and you have the polarization for free. So this would increase. We are talking with the source of 10 to the 13th to 10 to the 14th of muons, which you can get only in the neutrino factory type of beams. So in that sense, there will be a jump. There could be a jump with respect to PSI source of muons, or for example, the Brookhaven source. There will be a significant jump in terms of number of muons.
Okay. Yeah, the very last question. Could you explain more about relation between polarized muon beam and CP violation of neutrinos?
So I could go to my transparency. Yes. Right. Maybe this one. Okay. Yeah. So, first of all, the source, which is coming from the gamma factory, is symmetric in the sense that it produces the same number of mu plus and mu minuses. Now, what would happen if you would have polarized muons? If you would have polarized muons, then this is the distribution as a function of the fraction of the energy which is carried by the neutrino with respect to the mass of the muon x, and this is the angular distribution. So then, if you play with the polarization of the beam, for example, you can change. I don't know. Here you see for the nu mu for polarized plus one. Mu minus beam or polarized minus one mu plus beam would give you such a distribution of this fractional momentum for mu mu. For mu e, given this formula, you would get exactly zero if you would just sit at zero angle. So what that means that you can make the selection of separately, you see, by changing our beam from mu plus mu minus, you would have the mixed beam of mu e and anti-nu mu and vice versa by changing the sign of collected pions. But then by looking at angular distribution and the distribution close to the axis of the beam, you could actually choose the given proportion of anti-neutrino E with respect to, for example, neutrino mu, and vice versa for the opposite charge beam. So by looking at the angular distribution, you can control the relative proportion of electron neutrino, and this has to do with the parity with V minus A. Here you see structure of the weak currents. I don't know.
Okay. Yeah. Thank you very much.
I'm trying to explain this as quickly as possible.
Thank you. Okay, so let's move to the next talk, which will be given online.
Hello? Hello?
Mariana. Mariana, do you hear us?
Yes, now, yes, I do.
Okay, so you shared your screen.
Can you see my slide? Can you see my slide? Sorry, I don't hear you. Can you see my slide?
Yes, we can see your slides, so you can start your talk.
Okay,
Please.
okay. Okay, first of all, thank you very much for the invitation to speak online. I wish I could be there, but it was impossible. Okay, so the subject of my talk is a continuum solution to the hierarchy problem. So it's a little bit of change with respect to the previous talk, but okay, let's go. Oops. Okay, so what solution to the hierarchy problem? It was proposed, as everybody knows, by Lisa Randall and Raman Sundram in more than 20 years ago. And as you know, was based on a 5-dimensional space with anti-de Sitter geometry with line element given by this expression. This y is the extra coordinate in proper coordinate, and the metric in those coordinates is just linear in the proper coordinate. So there are two branes on this space. This is cut off by two branes, one the UV brane or Planck brane, and the other one the infrared brane or TV brane. And the typical scale in each brane, rho, is the let's say the TV scale is related to the scale at the UV brane, which is typically K. K is related to the curvature of the anti-de Sitter, by this Ward factor. This Ward factor has to be around 30 something just to achieve the proper hierarchy. Okay, so then you can use the ADS-CFT correspondence to understand some phenomena. And that's very useful normally. So, for instance, there are fields which are propagating in the bulk and which are localized toward the IR brane. In particular, they are the Higgs, they are the heavy fermions, and they are the Kaluza-Klein resonances. They are localized toward the IR brane, and in the language of CFT, you can say that they are composite or almost composite. On the other hand, fields which are localized toward the UV brane, the Planck brane, and are the light fermions, and they are essentially elementary. So this is just the language. This is just only the language. And of course, zero mode gauge bosons are flat in the extra dimensions. So this is just the theory. So you have a tower of KK resonances, which are on the TV scale, and then you have to probe this theory experimentally, and that's that's the origin of the problem. So this is what I call collider challenges. For instance, people have studied the production of tops, a pair of tops, TT bar, and they are not finding the signal, and as a consequence, the LHC data are putting severe bounds on the mass of the slightest KK resonances, in particular here for KK gluons. And those are two plots from on the right-hand side from Atlas and on the left-hand side from CMS. Both of them put bounds on the first KK resonance, which are, as you can see, of the order of 4 TeV for KK gluons. So that's really, that's a sort of problem, because these limits point toward the possibility that nature might have chosen values of rho. Rho is the typical scale, which is perhaps much larger than TeV, or that we have to reformulate our model. So I will now present 2 ways of doing that. Way number 1 is just that those strongly coupled resonances as KK gluons, perhaps they are not narrow, but they are broad resonances. So in that case, bumps flatten in detection, and they are more difficult, very difficult to detect. This is the way number 1. The way number 2, which I will devote most of the talk, is that resonances are really a continuum of resonances. So in fact, there are no bumps at all. Okay, so those are the 2 possibilities. So for the first possibility, the case that they are broad resonances, this is possible if, for instance, some fermion, in particular the right-hand at top, is localized toward the IR brane, very close to the IR brane, because the KK resonances are localized also toward the IR brane. And so they overlap a lot, and the coupling can be very large. And as a consequence, by decay of this KK gluon into TT bar, you can get a very broad resonance and very difficult to detect. This has been studied in that paper with my collaborators at TFI. And here I just present 2 simulations, one with a width of 10%, and the other with the width of 80%, and for a resonance of 2 TeV. So here you can see that in the 10% width, you can see a bump here, while if the width is 80%, so really you don't see anything. Okay, this is just to show that it will be much more difficult to detect. And if somebody is interested, you can look at this paper, but I'm not going to pay more attention to this solution. This is one of the solutions. Another more drastic solution is that KK resonances, as I said, are a continuum with a gap, of course, because experimental searches normally assume that new particles are isolated resonances. So this can be another possible explanation, I would say explanation in quotes, for elusiveness of KK states, that they are a continuum of states with a mass gap of around 1 TeV. Actually, this solution was proposed by Chavachaki 2 or 3 years ago. There are other theories in that direction, in particular the so-called clockwork mechanism or its 5-dimensional version, where in that case TeV is a different theory to what I will present, but TeV is the fundamental scale, and Planck is a Dirac scale. The KK must have a TeV mass gap and then a quasi-continuum spacing between modes around 30 GeV. This is also similar to other theories coming from string theories, in particular from little string theories, which are called linear dilaton scenarios, where the hierarchy problem must be solved by the string theory. Okay, so this is what I will study now. So I will study a class of 5-dimensional models. This is the class that we have considered, and then they share some properties. In particular, you can see this is the metric. It has 2 components. First, the Randall-Sundrum metric, and then a deformation which is very important in the infrared. So the properties of this metric, this is just a solution to the questions of motion. They reproduce Randall-Sundrum in the ultraviolet, and therefore they can explain conventionally the hierarchy problem with a fundamental Planck scale and a warped TeV scale. So from that point of view, is nice. It depends on a parameter nu here that you can see. For nu larger than 1, they yield a discrete Kaluza-Klein spectra with TeV spacing, which is the normal situation. For nu smaller than 1, they yield the continuum spectra without any gap, ungapped, and those are similar to unparticles that were proposed by Howard Chorchai some years ago. And then for the critical value of nu equals to 1, they yield a continuum spectra with a gap, And this is the model that I'm going to consider right now. So this was worked out long ago by ourselves, and just to see how for a theory with a graviton, the Schrödinger-like potentials, how they vary with this parameter nu. You can see here 4 panels with the potential, the Schrödinger-like potential as a function of here is the conformal coordinate. Here is for nu smaller than 1, so you can see that the potential goes to 0. This means that there is just a continuum, and there is a continuum with any mass gap. For here, this is the case nu equals to 1. In that case, there is just the potential does not go to 0, but to a constant value, and this is precisely the mass gap. And for the other cases, what you get is a discrete spectrum, because for nu larger than 1, you get the potential just goes to plus infinity at some point or minus infinity, and so they just produce a mass gap. So the critical case that I'm going to consider is precisely this one on the right-hand side of the upper panel. Okay. So the critical case nu equals 1 is just very special because it gives a continuum with a mass gap. So the Green's functions, in that case, they generalize the case of particle propagators. So the particle propagators, they have a real part, which in that case is the principal value of the propagator, and then an imaginary part, which in that case is just the delta function. In our case, what we will have is that the Green function has a real and an imaginary part. and the imaginary part is only valid, is different from zero only for values of p squared which are larger than the gap. Actually, this is the behavior of gap and particle, where the gap was usually produced by electroweak breaking. Here the gap is the TV, so it's linked to the solution. Sorry, it's linked to the solution of the hierarchy problem. And just to make it clear, the five-dimensional dimension has a UV boundary, an IR brane where the Higgs lives, and then there is a singularity at some value of the proper coordinate that I'm calling YS. And the mass gap is different for different bulk fields. So if you just take the different fields that will propagate in the bulk, you have gauge bosons, you have fermions, and you have graviton, radion, and the Higgs. So the mass gap is a function of rho, which is just this TB scale that I defined previously. And for the gauge boson, it is 1/2 of rho. For the graviton, radion, and Higgs is 3/2 of rho. And for the fermion, it depends on the constant C, which is the constant which determines the localization of the fermion. So C smaller than 1/2 corresponds to heavy fermion. C larger than 1/2 corresponds to light fermions localized towards the IR brane. So in that case, the mass gap for the fermion depends on this constant. So this is just sorry. So this is just a sample of spectral density functions that appear in the different cases. For the case of gauge bosons, the fermion, the radion, and the Higgs boson. So in all cases, you can see that, of course, spectral density is 0 below the mass gap, and then it has some particular shape. No, it has some particular shape which reflects the fact that there is an imaginary part. There is an imaginary part. Consider that this imaginary part does not correspond to the production of new particles, but it is like in the case of unparticles, it is just like that. Okay. So you can do some phenomenology with those things. As the mass gap is different, as I said, for the different states, the easiest produced continuum is for gauge bosons, because normally light fermions have C much larger or larger than 1/2. So you can just consider this produced at LHC. Normally LHC is looking for bumps in the invariant mass of the final state. However, here in production of fermions from Drell-Yan processes via gluon-Kaluza-Klein continuum, there is just an increase in the cross-section. So here I have plotted the ratio of the sigma at the partonic level. This is just at the partonic level, with divided by the sigma in the standard model, just controlled or propagated by the gluon exchange, for two different cases where the fermion that you are producing is localized towards the infrared, and for instance, the right-hand at top. Here you can see that this partonic cross-section is increased strongly with the energy. So at the end, you will have some enhancement of the total cross-section. And in the case that you produce a light fermion, which is localized towards the UV, so then you get a tiny enhancement, which will be much more difficult to detect. Okay, this is just at the phenomenological level, but there are some interesting things that can be studied by slightly approximating this model by another model, which, because up to here, all solutions were numerical. So we are trying to get some analytical solutions on Green's functions. And then for that, what we have done is to approximate the exact metric. Here you can see this is the metric that we were using previously. By
minutes. Give me 5 minutes. Please.
5 minutes. By an approximated one, where this is just, okay, this is Randall Sundrum, and this is the linear dilaton model. So you can see the difference between both metrics. The point is that one can explore the structure of Green's functions in the complex S-plane. That's very interesting because what you will find is that all Green's functions are inversely proportional to a universal function that I call here phi, which is just a combination of J plus and Y plus, where J plus and Y plus are combination of Bessel functions, as you can see here, and this function square root some square root which gives branches to the complex S-plane. So using that, you can look for resonances by looking for poles in the second Riemann sheet of the complex S-plane. So unexpectedly, we have found a tower of broad resonances located in the physical Riemann sheet. And this is the contour plot for the function phi, where you can see the location of the zeros. The zeros of phi are the poles of the Green function. And this is just a very good approximation where the location of the poles in the complex plane can be given in terms of the nth branch of the Lambert function, as it is written down here. So there are no poles found in the first physical Riemann sheet. So the poles are interpreted as resonances. So we are finding really resonances. And those are the location of resonances where this is the mass in units of rho, and this is just the gamma over m. So the location of the masses is very similar to the Randall-Sundrum theory, while the effect of unparticle is just dressing those resonances to provide them with a width which is very, very wide, very broad for the first resonances, but then it goes down to smaller values. So the same thing, okay, this was, okay. In general, what you have is, if you study this in detail, is that the Green's function can be decomposed in a resonant contribution where there are those resonances that I mentioned, and a pure unparticle contribution, which is corresponds to gapped unparticles with a dimension of the unparticles equal to 3/2. Okay. So this is some example of Green's functions and a spectral function for cases of Green's function for the UV, starting and ending in UV, and here for starting in UV and ending in the IR brane. So this this is the Green function, the absolute value of the Green function, and this is the spectral function. So the spectral function, you can see that there is a pole at 0 because those are massless. This is the case of massless gauge bosons, and after that there is a structure. This is those are the spectral functions. Something that I would like to mention is that while UV is positive definite, as it is the 4-dimensional spectral function in the UV brane, the case of UV IR is not, and this apparently challenges the physical interpretation of the spectral function in 4-dimensional quantum field theory. This apparent contradiction can be resolved by noticing that this spectral function can be considered as the matrix element of an operator in an infinite dimensional space, parameterized by the coordinate y. And this matrix, rho hat, turns out to have a factorizable form. So it's a factorizable matrix. And as such, all eigenvalues are 0 except 1, which is just a trace, and which is positive because the square is the sum of squares. So there is no contradiction there. The same thing can be, I have done the same thing for massive gauge bosons. Okay, you can introduce the mass of gauge bosons, and then you find the same structure of poles, a similar structure of poles, very similar. And those are the Green's functions, or the inverse Green function, where you can see that they vanish precisely at the mass of the C, because this is for the case of the C. And those are the corresponding spectral functions, where you can see that there is a delta function corresponding to the mass of the C, and then the continuum. Okay. Something similar can be done with Dirichlet boundary conditions. For instance, if you have in the bulk an SU2R gauge group, just to protect the rho parameter, the custodial symmetry. And okay, this is very similar. For phenomenological applications, is the same as I said before. I have plotted here a comparison between the exact model, which is a continuous line, with the analytical model, which is the dashed line. So in principle, they are a good approximation to each other, and qualitatively, the similar is the same. Of course, if you want to go to the hadronic cross section, so you have to integrate the PDFs. And integrate over S hat and the rapidity, and then this is the usual thing. So this is some work in preparation. So to compare with experimental data, we have to think strategy, because perhaps we can assume dominance of the first resonance, or perhaps or introduce all the continuum there. So this is just work in preparation. Okay, conclusion. So. Warp extra dimension is an interesting alternative to solve the hierarchy problem. There is no doubt of that. One exploring possibility, as I mentioned, to solve the elusiveness of signal at LHC is that KK modes are very broad, triggered by fermions localized towards the AR brane. Another most intriguing possibility is that there is a continuum of KK states related to CFT and particles and so on. In particular, the 5-dimensional model with a continuum is pretty unique. As we have seen, it corresponds to a critical value of the metric parameters. And in fact, it is a 5D modelization of conformal theory with a mass gap. Green's functions, as we have seen, behave like those of particles, which means that they have an imaginary part not corresponding to particle creation. And in general, Green's function can be decomposed as an unparticle component and Green's function with broad resonances, which pole in the second Riemann sheet of S. As I said, the location of masses is very similar to that in the Randall-Sundrum model, while the width is very broad for the first resonances, while for heavy resonances it's narrow. As I said also, confronting this theory with LHC experimental data is in progress. And there are also plenty of theoretical problems to be understood. There is some work in progress here, and for instance, unitarity of the theory, spectral densities, and things like that. So this is really a new field that needs to be explored, although many things have already been done in the past. And so, okay, so thank you very much for your attention. Thank you.
Questions from audience? Yeah, Matthias, please.
Mariano, thanks a lot for this really nice talk. So I just had a question on the models that you were discussed with the modified metric. Are these, is it known whether these are solutions to some Einstein equation or whether they are consistent with the equations of?
No, they are solutions to the Einstein equation. So we have introduced by steps. We have started from a superpotential, which is the simplest way of taking into account solving those equations, and then we have defined a superpotential, which is the input function by steps, and then we have solved the 5-dimensional Einstein equation, taking into account the jumping conditions and all that. Yeah. No, they are a solution to the Einstein equation, Matthias. Yes. Thank you for.
You introduced. So you really have a whole class of solutions, basically. You have this parameter nu in the extra term, the log piece in the metric.
Yes, yes. But this, okay, this comes from really, okay, the way we have proceeded is the following. So you introduce some pre-function, which is called a superpotential, which has nothing to do with supersymmetry, as you know. It was introduced by Gapser and others. And there you introduce the parameters there. So this is just the input parameter. Of course, you can also introduce the bulk potential as an input, but it is much more difficult to do that. So in principle, those parameters are external parameters. And then for a general and arbitrary value of those parameters, we have solved the Einstein's equation of motion. Yes. So this is my models are solutions to are really backgrounds of the theory, you know, and they are really backgrounds of the theory. Yes.
Thank you very much, Mariana. I don't see further questions, so thanks a lot.
Okay, thank you. I will, I will unshare the stop share. Yes. Okay. Okay. Thank you.
Yes.
This is here. Okay, good.
Okay, so you go this to the next one.
Yeah.
With this you go to the previous one, and here there's a pointer.
Pointer, yeah. It's not. Yes, thank you very much. First of all, I wish to say how happy am I being here, having a chance to participate in person in this meeting. So thank you to the organizers. My intention is to share with you something that is light, pleasant, perhaps interesting, and maybe surprising, maybe even useful at the very end. So let's start. I'm going to talk about T-channel singularities. Next slide will show what they mean. And this is the outline of my talk. And this is based on a recent short letter with Michał Igliński, who is a PhD student, and Stanisław Mrówczyński, who is a fellow in Warsaw. But it's not going to work.
Yeah, it's not, yeah, this
Yeah,
one.
it's this one. Yeah.
Can you point here?
Okay, so I have to point here. Good. So let's consider a binary process like that, 2 into 2. The matrix element is proportional to just 1 over t minus m squared, where m is the mass of this mediator. And if you calculate the total cross section, you integrate the square of this matrix element, then if t could be equal to m squared, you can hit the singularity and get divergent cross section. Perhaps your first instinct would be, no, it's impossible because t is negative. We know that. No, but t is not always negative, as we will see. So the condition, the pole condition, t equal m squared, corresponds to something physical, which is an angle between 3 and 1, and the cosine of this angle is given through its energies in this way. And one can easily find a condition for s, or square root of s, such that this quantity is less than 1, and that will provide a region of s in which there is a singularity. So if s is in this range, s1, s2 are given in terms of masses, exclusively in terms of masses. Alpha is capital M squared is the mediator. These are M1, M2, M3, and 4 in a standard manner. Okay. It turns out that this, first of all, the elastic scattering. Certainly, if M1 is equal to M3, then indeed T is negative and there is no, so for elastic scattering, there is no singularity. However, in other cases, in general, there is a singularity. And it turns out that the condition that I showed you before could be reformulated in more physical terms, namely T-channel singularity appears if and only if exactly one particle in the initial and in the final state is unstable and the other is stable. Here, stability means decays with respect to the interactions that are drawn here. So one option is the following, that M1 is larger than M plus M3, and this decay is allowed, this 1 into 2 decay is allowed, but there must be another condition, namely that the scattering of the mediator and M2, or inverse decay, can produce M4. That means that M4 must be larger than some of those two. So that's the one option, and another option is from the other side, or from the bottom, right? The M2 is decaying, and M1 is scattering on the mediator. It actually turns out that this is a special case of so-called Coleman-Norton theorem. Now, let me show you standard model examples. There are examples. I mean, for us, it was surprising. So I'm not sure if, perhaps for you, it is obvious, but for us, it was surprising. So So how do we draw those diagrams using those conditions that we know? We take a process that has one stable particle in the initial state and another one stable particle in the final state, and the masses must be right. So these are, for instance, these are not the only. For elastic scattering, processes like that will have T-channel singularity, and inelastic scattering examples are shown here. And in fact, in hadronic processes, this has been noticed long time ago by this gentleman, you see 61, but that was hadronic. But in the electroweak sector, this, which one is this? It's this one. No, yeah, it's this one. This process has been noticed by Apostolos and Marek Nowakowski long time ago, again as a source of T-channel singularity. So we have discovered those papers, of course, after we good. So what is our natural instinct to do in a case like that? I mean, the natural instinct tells us that we should do resummation, right? We calculate 2-point functions and we sum them. We get geometric series, like in Breit-Wigner case. And that's in principle possible. However, and those examples from the standard model were chosen. You see how what was here? The mediator here within the standard model was always stable. So that means that the Breit-Wigner for those diagrams doesn't help. Breit-Wigner doesn't help. I'm sorry, but I'm having troubles with this. Okay, this is previous page. So Breit-Wigner doesn't help. I think I jumped over one page. I'm very sorry. So let's look more closely at the process of elastic scattering of Z on electrons into electron and Z. There are 3 diagrams. The one that has a T-channel singularity is this one. And in fact, this process is interesting because it is a weak analogy of the Compton process, where photon is replaced by Z. And it's easy to calculate the differential cross-section, d sigma over dt, and integrate that. And indeed, there is a region of S. You see, this is total cross-section plotted as a function of square root of S. And one can calculate those limits, S1 and S2. They show boundaries of the region where cross-section is divergent. And here, what is shown on this plot is just the one branch. S1 is here, and here starts the region of divergence, and it ends far away at the square root of S2 equal mz square over m electron, which is huge number. So it's not shown here, but indeed in that region the cross section is divergent. Okay, and now I can come back to Breit-Wigner, and you see it's clear, right? Because the imaginary part of the self-energy gives the width, and if a particle is stable, then there is no cure. There's no regularization. The divergence is still there, and our intuition suggests that the source of those difficulties is the fact that the asymptotic states for unstable particles cannot be defined. So that is what our instinct suggests, and therefore our colleague Ilya Ginzburg, a long time ago, in the context of muon colliders, noticed, I think he was the first who noticed that the process that is shown on the next slide, I believe, yeah, that the process mu plus mu minus into W plus and W star is indeed divergent. The cross-section suffers from T-channel singularity. And Ilya tried, of course, to cure it. And what he did was he proposed something quite natural, right? The wave function of this initial particle in the rest frame is just e to imt. And he said, since this is unstable, let's multiply that by e to minus gamma t, because to include this suppression, and that implies complex mass. But this was too straightforward. I mean, it doesn't work. It's easy to see that there are certain constraints necessary, like the width of 1 and 4 must be the same in order to make it consistent. And there are other difficulties discussed by those gentlemen. So other people who worked on that was Melnikov and Sebo, and in '96, and later on Ronald Kleiss and Dance. So what they did, they took into account transverse distribution of the beam. If the beam has a shape, if it's not a plane wave, as we usually do, but it has a shape, then indeed that could be resolved, and the cross section is finite, and it boils down effectively to replacing this kind of integral that contributes to total cross section by that one. Note that there is this capital pi that appears with minus here and plus here, and this pi is proportional to 1 over a, where 1 over a is the beam width. So if the beam width goes to infinity, then pi goes to 0, and we reproduce the standard thing. But that for colliders, that looks like a solution. Now, we have encountered this singularity working on two-component dark matter, vector and Feynman dark matter, and we were using micromegas, I think, and we were getting infinities, divergent results. And then so we were digging, looking for that, and we discovered those T-channel singularities. And of course, this cosmological constant, the method proposed by Melnikov and Sebo is not applicable for in the cosmological constant, because this is not a collider, but it's a collision term for Boltzmann equations, where we have a thermal bath and particles propagating in the thermal bath. And in fact, you can think about this phi, this mediator, as traveling through the thermal bath. So we thought that that's probably the good way to go. And it's known in thermal field theory that the masses and widths will be generated for non-zero temperature. So here I will show you simple calculation using toy models of 3 scalars, phi 1, phi 2, and the mediator that is this capital phi, and the interaction term does this cubic interaction term. And it's not difficult to see that non-zero imaginary part of self-energy emerges as result of thermal interactions of this mediator with the medium of particles in thermal equilibrium. This is a formula for this one loop diagram with propagators written here, and this could be notation is as follows: that beta is usually 1 over t. F's are distribution functions. So again, this is this 2-point function, and what we need, in fact, is an imaginary part of that. Know that it depends on temperature, but it also depends on absolute value of p in this case. And the result is given here, and indeed that generates. This is non-zero. That generates effective width for this particle for the mediator, and here there is an approximated result which confirms what we expect, that it should vanish with temperature going to 0. This is 1 over beta, so proportional to t. So it indeed does vanish. Good. So just to say again what I believe is clear, we include this sort of diagrams plus multiple insertions of that 2-point functions, and therefore this divergence is replaced by a result of that sort, and we need the sigma for various constant values of P13 is shown here. Yes, thank you. And I'm nearly done. And the illustration is here. We calculate because of our applications, right? The other applications was the collision term for Boltzmann equations, where thermally average cross section is essential. So this is a calculation of thermally averaged cross section, including this thermal width contribution. Masses are specified here. Vertical axis gives you cross section. Horizontal is x is m over t, and those colorful lines are lines drawn for constant width, and the width is shown here. So going upwards, width is decreasing. And this is something that we understand, right? Because in the limit of 0 width, this is divergent, and those red dots that shows the real behavior of this thermal average. And indeed, when x grows, that means t decreases. We expect singularity to be present, and another scale shows it even more explicit. So very good. So what I showed you is presence of T-channel singularities and the conditions for T-channel singularities to appear. And then I also showed you standard model examples, including this analog of the Compton scattering. And in the case of colliders, it seems that the solution proposed by Melnikov and Serbo is the right one, or at least it implies a finite result. However, for cosmologists, for cosmology, we are advocating this thermal width. And now, as I said, that we encountered those singularities working on some multi-component dark matter, and indeed the dark matter physics is the place where those singularities naturally appear, because we need stable particles. So there are particles that may appear in the T-channel here, and therefore standard Breit-Wigner regularization is not really working. And the very last comment is that, you see, even if the singularity is regularized by the width is a loop-generated width. So still the cross section is much larger than naively one could expect. Good. Thank you very much.
Thank you very much, Bogdan. Questions, please.
Philip.
It's a question from the experimentalist. About this singular standard model process, because I'm not sure I understand, because in my feeling, the process cannot be singular. Your cross-section calculations can be singular.
No,
No, but it's not the same.
certainly. Physics is finite. Yeah, I agree.
So, or there is, or no, because it could be that there is some physical reason why this process above some scale is meaningless. But I understand this is only that your calculations are not valid, and the physical processes should be finite, yes?
Of course, therefore we are seeking the regularization that would make it finite. However, I mean, the physical reason or for the convergence is pretty clear. I mean, everything is on shell. So the decay 1 into 3 and mediator is on shell, and the 2 scatters on the mediator and produce 4 as an inverse decay.
Okay.
This is just physics.
It will be as in the simple Coulomb scattering, that the cross section is infinite.
But it's not. It's a different singularity.
Thank you.
Apostolos, whatever.
Okay, that's right. So it's a singularity that naive standard calculation methods do not work. I'd like to make the following comments. So first of all, the singularities appear when you have two stable, absolutely stable particles crowded to n. You never have that singularity. We came to this singularities because we tried to analyze a vector boson approximation, not like Weitzer-Williams, but a vector boson approximation. A very big story, but so that's the first thing. So we have, however, when we have 3 to 3, and it's 3 particles scattering to other 3 particles scattering, it's not a collider experiment, it's a different experiment. I can see that could appear in the technological consideration. The solution that these people proposed, they think that's correct, but it's not correct because they failed the positivity constraint. If you see, they have 2 singularities, they're shifted. You have a double pole, which you shift. If you look at your slide, you have the poles have been shifted left and right.
Yeah, but you're referring to Melnikov and circle. Yeah,
You are
right.
referring that the solution is not solution. For me, at least, maybe for them it is. So that is a PRL for them, but for me it's not. And I can tell you that because then you take a phase. If you have an absolute, you have an infinite resolution, detector resolution, so you can go and look at the phase space and cut the phase space. You can see, you can still uncover the singularities between the minus epsilon A and plus A. And this is not positive. That means if you add the 2 phase spaces, it's not the sum of the 2 phase spaces. So there's a do not satisfy the positivity constraint. It goes negative between the 2 poles. Right. So the other thing which we noticed, sorry for the long. We noticed is that what we noticed with Novakovsky, we said that this process is non-local. What means that? This means that this process at some point should not be considered as a matrix problem like that it is, but because the particle becomes on-cell and it could propagate very far away, it should be considered like neutrinos. You have to have a mixed representation of space and time. I believe I can solve that problem in a different way in this case. But no, this is not the solution to this discussed there. And finally, my last comment is about thermal field theory. We know, I know the referee of your paper, don't worry. In the thermal self-energies, you have absorptive parts before the onset condition. This is already documented. Because what you need is you need an absorptive part below the not from 1 to 2 by 2 scatters, and we already know that already exists. But I mean, it's documented in textbooks like
but then this is but then this is two-loop contribution. Here it's one-loop contribution, and it's exactly the same interaction that is responsible for non-stability. Therefore, it's an attractive feature of that.
And you also have another similarity equal 0.
Now, in this example, no, because electron mass was 0. That's why there is no singularity at 0.
Okay. Mariana had a question. Mariana, you still have a question?
No, it's okay. It's okay. It was already answered. Sorry. It's okay. Thank you. Thank you for your talk, Bodan.
Okay.
That was it was a pleasure.
Okay. Thank you, Mariana.
Thanks, Mariana.
Anybody else? Okay. Thank you very much, Bob.
Okay, thank you.
Thank you. Okay, so we are coming for the last talk in the session. Karim Benakli on dilatonic anti-de Sitter black holes and weak gravity conjecture.
Stop saying to spread there.
And then I have to do you hear me? Okay. I can start. So let me first thank the organizers for invitation to this session of this very nice set of conferences in Corfu. So I will be talking about black holes and weak gravity conjecture. I'm trying not to be too technical, just put equations that are needed. This work, there is a first part done with Ignatios Antoniadis, and the second part, which is done with my two students, Carlo Branchina and Gaëtan Laforgue-Marmy. It doesn't work. Let me. No. Right. Yes. Okay. Okay. So let me start by reminding you the weak gravity conjecture. This was proposed in 2006 by these guys. This is very simple to state, and it says that there should be in your spectrum some state for which the charge is bigger than the mass. So charge usually doesn't have a unit, mass has unit of mass. So in this equation, what is the charge and the mass are something which have been converted into length units. And it tells you that the extremal case is this: mass of a charge equal to 1 will be this quantity in terms of physical quantities, where here you have the Planck mass, should be 1. And the weak gravity conjecture says that you need to have a state that has a charge bigger than the mass. It doesn't tell you what is the mass of this state, if it's in the effective field theory or if it's some composite state, some super heavy state, whatever. It just has a charge bigger than its mass. This weak gravity conjecture in the original paper was motivated by gotten by considering different requirements, and they always lead to this statement. Either you say that you need to have a super extremal state. Extremal states are those for which charge equal to mass. Or you need to violate the PS condition, which says that the mass is bigger than the charge. Or that you think about Newton force due to gravity and Coulomb force due to electrical charge, and you say that the Coulomb force is bigger than the Newton force. Or you say that extremal black holes, the black holes that have charge equal to mass, can decay, and you look at kinematics and you can see very easily that you need states which have charge bigger than mass. So different ways, different requirements all lead to this condition. And this condition also implies the absence of global symmetries that we know should not be there in quantum gravity, and so this looks very fine. But all these states which are equivalent when you have just flat space-time, you put Einstein, so you put the Newton force and you put Maxwell force and Coulomb force because you go on shed. And so this is, they all give the same thing. But when you have a theory which is a little bit more complex, you have other interactions, and then these statements give different conditions. So which one of them is the correct requirement to get the weak gravity conjecture? Maybe none of them, maybe all of these are just consequences of some more fundamental requirement in the quantum gravity theory that tells you that you have to have this condition satisfied, and then all this will come down, will lead to this condition. Nowadays, the condition that is taken most of the time when you have more complex situation is this super extremal state exists, and this is what I will take for the rest of this talk. And this is what will allow me to get conditions that will be matched to this one when I simplify my theory. So what I'm going to consider. Sorry? Yeah, this is what I use here. This is so this is 1/m Planck. Okay. Yeah. So then everything is in length unit, in Planck length unit, if you want. Yeah, it is here. It's converted. So everything is converted. So what I wanted to consider is having a vacuum energy. The simplest way is having cosmological constant, because we know that in our universe there is a vacuum energy, and I would like to know how this Wigawski conjecture is modified when there is a vacuum energy. I will try to do more, like 2 shots with 1 stone. And also, I would like to introduce a Dirac uncoupling to the Maxwell field. So F square is U1 strength field. And for this Dirac field, I will consider that there is a potential. So I consider the theory given by this action, which is the Einstein-Hilbert term, the kinetic term for the Dirac uncoupling to F squared, and the potential for this Dirac. The strategy to get the weak gravity conjecture condition is usually is this one. You construct black hole solution for your theory. You look at the solution, this black hole solution, what is the mass and charge, how they are related in the solution. And you try to find what is the relation when you are at the extremality. And then you say you want to have super extremal conditions, so that you get the super extremal condition that we identify with the weak gravity conjecture in this theory. Extremal means the largest charge that this black hole can have. But I will be more specific. So this is the way it's done everywhere. You can find it in hundreds of papers. For the case with non-cosmological constant, you write is a neutron black hole. You have the 0, component of the metric. You say you don't want to have naked singularity for your black hole. And this tells you that the black hole should satisfy this condition, charge smaller than mass. And so you want to have super extremal, means you have to have Q bigger than M, which I wrote in the first slide. If you just added in, without cosmological constant, you just added this Dirac, then you find that black holes exist if you have this condition, which is satisfied. Here is strictly smaller because one of the surfaces of the Reiner neutron black hole is a singularity now, and so you just take the inverse of this inequality as the condition of having weak gravity conjecture in this theory. And this is what was done by these people. So we want to do that when lambda is different from 0. I said I would like to put potential for the Dirac. The simplest potential that people started looking at a long time ago for this Dirac is this Liouville kind of potential, but this doesn't have asymptotically de Sitter or de Sitter black hole solutions. While I would like to have the most symmetric black hole solution, I want to look for de Sitter or de Sitter asymptotical space. And so this potential is not good. Fortunately, some people found a potential that has black holes with which are asymptotically de Sitter or de Sitter. And when you have a Dirac, and the potential is this form, which is a little bit complicated, but not so much. And the black hole solution, then you can write it, and the metric has this form where you have this R plus and R minus of some integration constant. There is a term which depends on the cosmological constant. It's here. And the Dirac is this form which has this singularity at one of the integration constant. And this is the usual field strength. This is the solution. And we are going to discuss it by taking the simplest to the most complicated case, slowly. So I say there are two integration constants, R plus, R minus. This have to be related to some physical parameters, and it's important to keep in mind that there are two physical parameters, the mass and the charge. There is a scalar charge that you can define either through this integration of the flux of the scalar, or by looking at the behavior of the scalar field as function of R. But this is related to the charge and mass. And so there is only two parameters for this class of black holes. And so they satisfy the no-hair theorem that says with mass and charge, you can classify all these black holes. So let's start with the simplest case, which de Sitter and no Diraton alpha equals 0. This metric simplifies to the one that is known since the 90s, done by Romans. And you get a solution which has three horizons. One is the Cauchy surface, which is located at R minus. One is the event horizon, which is located at R plus, where the metric change becomes time-like becomes space-like, and vice versa. And there is a cosmological horizon. Above this horizon, the force due to cosmological constant, which is a repulsive, dominates, and inside it's the gravity is attractive. The location of horizon depends on change when the mass and charge vary. So for generic black hole in this space, I say there are three horizons, and these two horizons might coincide. This is the extremal black hole, and this is the ultra cold black hole in the 9 black holes. I will come back. So I'm sorry that in my computer there are colors, but in the projector doesn't show them. The phase space is that you have the black hole solution is inside this deformed triangle. If you are on this side, means the charge is too big. You don't have black hole, and here you don't have black hole. So if you increase the mass, this is what I described. If you increase the mass, the event horizon starts to increase, and at some point your black hole eats all the Sitter arch, so which is not allowed. If you increase instead the charge, it's the Cauchy surface that starts to increase, then you reach the external black hole, and beyond that, the solution giving this horizons become complex, and you finish with a naked singularity. So this is going this way to the right. And if you remember, the condition we got to conjecture was by having the biggest charge. So you see that this green line will become the condition for the weak gravity conjecture in the Sitter space. So this is this area is the area where you have weak gravity conjecture state should be, there should be some state populating this region. For lambda bigger than 0, you can take the case alpha equal 1, which is the easiest one. And in this case, it's solving a polynomial of degree 3, which you can do, which is not a big deal. Sorry, some curves don't show on the screen. I don't know on Zoom if people see them. But you have different possibility for an equation of degree 3. This is a simple math, so you can see how many horizons you have. And then you have this kind of diagram. Instead of the one on the right, you have the one on the left. And you see that from 3 solutions, you have one solution which is now a singularity, and you have either 2 or 1 solutions. And because of time, I'm gonna speed a little bit. So the case alpha different from 0, it is generic, is harder to solve because it's no more a polynomial. So it's some function which have these alpha powers which are totally arbitrary. And so the way to solve it is to decompose G00 in 2 functions and study the intersection of these 2 functions. And you find that for alpha bigger than the square root of 3, there is no maximal mass anymore. You never eat all the Sitter space. It's the Sitter patch. This is one peculiarity that I want to mention. Increasing the charge is very similar to what you had before, and you find the extremal black hole solution, which are given by this line, and you can identify it with the weak gravity conjecture condition, being on the right of this line. The case alpha is 1 over square root of 3 you can solve, and we have a new extremity condition. But the case of alpha compiles between 0 and 1 over square root of 3, something happens is that you never reach extremality. So what happens is that your metric becomes complex before you reach extremality. When you approach this Cauchy surface, which is a singularity, increases, but it never reaches the red curve, which is the horizon. And in fact, the metric becomes complex before it reaches it. So you never find extremal condition. So to summarize the extremal black holes, you have that for alpha bigger than the square root of 3, you find exactly the same condition as in flat space-time, and you can say, okay, the weak gravity conjecture didn't change. For alpha is equal 1 over square root of 3, there is a modification due to the cosmological constant, which go to 0 when cosmological goes to 0, when you will recover the flat space-time. This is the same thing for alpha equals 0, but for alpha is compared between 0 and 1 over square root of 3. We never reached extremality. There is no. So you find the condition for the black holes, but this is, I will not say this is a condition for weak gravity conjecture. Let me skip this. And you do it also for, okay, I have time. Okay. So let me tell you this. We also computed for taking black holes as point-like particles far apart, the interaction between these black holes. And you can look when they are repulsive, attractive, when the interaction between the 2 black holes considered like point particles vanish. You find that this always happens for this value, which is the same one as the flat space-time. But what happens for alpha between 0 and 1 over square root of 3, where the metric becomes complex, there is another point where the forces will compensate if you don't take 2 black holes, but if you take a black hole with some orbit which has this dependent on the dilaton, so like a Kaluza line. The case of under the Sitter is a little bit different because now you have always this 1 over square root of 3 is some value which changes the behavior of this condition for extremality. But now you have less singular surface, less horizons. Instead of having 2 horizons, you have only 1 in this case. While for alpha smaller than 1 over square root of 3, there are 2 horizons. This case was partially studied by Rob Myers and his collaborators, just in some limit, and by Friedman and people I cited before, Elvong, Friedman, and Liu. But they looked just, and they have the similar conclusion. But they looked just for some limit. So this is what in figures what I said before. This value of 1 over square root of 3 seems very special. It separates the case where you have just one singular Cauchy surface and one horizon from one singular Cauchy surface and 2 horizons. So I just conclude. Motivated by extending the weak gravity conjecture to the case of non-vanishing vacuum energy, and we know in our space there must be something which looks like vacuum energy. We investigated external black hole solution in Einstein-Maxwell dilaton theory, and we found that for alpha very small, these black holes look like Reissner-Nordstrom black holes, while for alpha big, behave like Schwarzschild black holes. And we found that there is some value which is 1 over square root of 3, which is very peculiar and separates different phases with different behavior of external black holes. For ADS, there are always the external black hole solution, and we find the generalization of the weak gravity conjecture that goes to the original one in flat space-time when lambda goes to 0. But for DS, the sitter, our solution don't give external black holes in the case where alpha is between 0 and 1 over square root of 3, as the metric becomes complex before we reach extremality. Thank you very much.
Thank you very much. Please. Yes.
I don't know so well the rules of the gravity conjecture. It looks to me that a condition comes out of string theory constraint. And okay, the question I'd like to ask is the following: can I have any potential for in your view of phi, or you are analyzing particular class of potentials and you draw your weak gravity conjecture?
Let me tell you. First thing, weak gravity conjecture and string theory. The weak gravity conjecture was the formulation doesn't use string theory, but then you check that string theory that is your model for quantum gravity satisfies this. Now, the potential I wrote for some values of alpha, you can understand it as coming from string theory. So first, for onto de Sitter, for some values of alpha, you can make it supersymmetric. You can see it comes from supergravity, etc. For generic values of alpha, then for generic values of alpha, I don't know if you can have it from string theory. Already in string theory,
let's say I know the feeling of string theory and I can throw a potential there.
Yes.
What can you tell me about that?
What the potential?
Yes. Phi square, phi cube, phi 4, like Higgs potential.
I mean, you write potential. You have scalar fields. You write potential. Then you want string theory to tell you something about the potential, or
I'd like to know whether there is a conjecture or a constraint that comes from top down. If there is a constraint that I can't see, then
no, you can okay. There are conjectures about potential for scalars in string theory. But for example, there is this conjecture, maybe you are thinking about this, the Sitter doesn't exist in string theory, but yeah, but okay. First, the Sitter, what the conjecture says exactly is that the Sitter cannot exist as stable, but it can exist for some time. So, and this time is it can be very long for a small cosmological constant. It goes like h log h. So you can say you do it. Yeah. So that's first thing. Then you have also arguments by people who look at de Sitter conjecture a different way. But even if it is quintessence, this kind of arguments might still hold as a good approximation. So if you are thinking about this, this is the status of the thing. And conjectures, there are many conjectures about Swampland conjectures.
Yeah, thank you. One more question. Yeah, two.
Can this conjecture be applied to in modified gravity theories or just Einstein gravity?
I mean, the way it's done, this is what I try to explain, that you take your theory, and then you have to say what is the principle that you should satisfy, and look in your theory what is the condition so that you satisfy this principle. So the weak gravity conjecture, I don't think we know exactly the fundamental principle. But if I take that this existence of super extremal state is the guideline, then you take your modified gravity and you construct the extremal black holes, and you say, okay, I want to that the condition that some super extremal state exists, and you find the condition. Okay.
Yeah, Gustavo.
I would like to ask whether these ADS black holes are supposed to be taken seriously in the sense that they should be found in experimental to be found in the universe. And we test whether they exist or not. Experimental, my observation.
I mean, if you think our space-time is de Sitter, it has a cosmological constant, then black holes that are in our space-time are this kind of black holes that are not with this dilaton, but maybe with alpha 0. So yes.
Are there any plans to look for them?
Now, we know about black holes, but our cosmological constant is so small. I mean, the effect is very small. So, look, we do all kinds of physics. Yeah, positive. Yeah, de Sitter, I say. Onto de Sitter is just academics. And de Sitter, then the cosmological constant is so small. So, I mean, the effects are negligible. I mean, we do everyday experiments we check laws that we have built by assuming Minkowski space-time. No?
So it cannot be falsified like this.
Excuse me?
Cannot be falsified this.
This is not true forever, but for now, I mean, there is first, I don't know how you can measure effects of cosmological constant in black holes, but then there is the question of cosmology, where in the past the vacuum energy was larger, and where you can maybe have some effects that you can see from this condition.
Okay, I don't see more questions, so let's thank Karim and also all the speakers for a nice talk today. Thank you very much.
There was no question from the, we didn't check. No.